Hello everyone. Today we will be presenting the paper FedRL Improving the Performance of Federated Learning with Non-IID Data uh, by Yufei Kang, Bo Chong Lee, and Timothy Zile. So if we talk about the conference background, uh, the paper was published at IEEE GlobalCom 2022, one of the flagship conferences of the IEEE Communication Society, held in Rio de Janeiro, Brazil, from December 4th to 8th in 2022. The conference theme was Accelerating Digital Transformation Through Smart Communications. And this paper appears on pages 3023 to 3028 and has received 7 citations to date, indicating its relevance in the federated learning community. The first two authors, Yufei Kang and Bo-Chang Lee, are from the Department of Electrical and Computer Engineering at the University of Toronto, while Timothy Zile is affiliated with the Huawei Technology Canada, showing this is a collaboration between academia and the industry. What is federated learning? Let me start by explaining federated learning. Imagine you want to train a machine learning model using data from thousands of smartphones, but you can't collect the data due to privacy concerns. The federated learning model solves this by allowing multiple client devices to collaboratively train a shared model while keeping their data local. The process works like this. Each device trains a local model using their own data, then only sends the model updates, not the raw data, to a central server aggregation. The traditional approach of this method is that the standard method called FedAverage or federated averaging, which simply computes the average of all received model updates to create new global model. The non-IID problem, which is the main problem we are trying to solve. This brings us to the core challenge this paper addresses. In an ideal world, we'd have IIID data that is independent and identically distributed data, meaning each client's data come from the same distribution. But in reality, we have non-IID data. For example, if you're training a photo recognition model used in different countries, users in different countries might have different types of photos. This non-IID distribution causes traditional federated learning to converge slowly and achieve poor model accuracy. This sets stage for why we need better solutions, which my colleague will now discuss.
Thank you, Hasi. Let's go on to the next slide. Yeah, Hasi, can you please go to the next slide? Yeah. In the previous sections, we established the foundation of the federated learning and the challenge of the process non-IID data. So now let's examine why the existing solutions for the short and what are the research community has attempted to address these limitations. So let's start by the examination limitation of the current approach. The most widely used algorithm like a FedAverage work reasonably well in the homogeneous cities where the data is evenly distributed across the clients. However, when we introduce the non-IID data distributions, which are the non-real-world scenario, FedAverage become the so significant weakness. So look at the CPAT experimental present in the paper. We can see that stark performance gap versus non-IID settings. Adams and Atlantis saw only the marginal improvement over the standard FedAverage. So even more trouble in the when we compare their performance and non-IID settings, where the average performance is ideal IID conditions. We seek significant regressions of the both accuracy and convergence speed. This aggregation simply adapting the centralized optimization method with federated learning isn't sufficient to handle the complexity of the heterogeneous data distribution. So go to the next slide. Yeah, next slide, please. So, what's the real happening under the hood? So, authors identify fundamental issues that the previous work had overlooked. The that the memory loss problem is adaptive optimization method. Here the core issue is adaptive optimization method really exponentially moving average or EME make the learning rate of adjustment, while EME provide the fast convergence of focusing on the recent gradients. It's come at the cost. So these methods lose critical hit historical information during the aggregation process on the server side. Think about this way. In the traditional centralized trading, and optimizers like Adam maintains complete history gradients statistics. But the better learning when you aggregate the client updates on the server, we will essentially start in the fresh each round without leveraging the rich optimization practices that could perform the better decisions. This creates the better fundamental balance collages. On hand, we want to pass convergent behavior that come from the EME-based methods. On other hand, we need to leverage the past optimization techniques to make the information decision about the when declaring and convergence properly. Current methods struggle to strike this balance, especially in the high dimensional settings. We grant the we grant the various timed is large exactly the condition we find the better learning with non-IID data. So let's go to the next slide. Next slide, please. Yeah, the research community has approaches this problem from the multi-angle, and it's worth categorize these efforts under the where gaps remaining. First, we have server-side improvement method like a PET average, PET AVGA may introduce the momentum to the server aggregation process, while PET-opt framework provide the general structure of the incorporating the adaptive optimization. These approaches focus on improving the aggregation mechanism itself. And the second, the client-side modification. An algorithm like a Petbox has comfort at regularization term to control the various local training objective. While these methods can reduce the client difference, they come with the additional computational costs and parameter tuning requirement. Third is the structural approach that attempt the neuron matching at the coordinator of the layer level before averaging. However, these methods limit the specific neural architecture lack of the general applicability. So, despite this divergent networks, the critical gap remaining. The lack of the long-term memory, like server aggregation process, none of these existing methods adequately address the fundamental memory loss problem at the occur when adaptive optimization methods are applied to the data learning. So, these analysis we are motivated to go to the new approach because they introduce the predator learning. So I hand over to the Janagopan to introduce the PED to continue these presentations.
Thank you. Thank you, Savinder. Now I am going to present about introduction to PET-RL. So first of all, let's see what is PET-RL. PET-RL is the deep reinforcement learning framework built to enhance the federated learning system. Unlike statistic aggregation methods such as PET-average, PET-RL introduced intelligence called deep reinforcement learning agent into the server-side aggregation process. So, DRL agent is used to dynamically adapt hyperparameters during training, which helps in improving convergence speed and final model accuracy without adding any extra communication burden to the client side. So let's move on to the next slide. Yeah, now let's see FedRL algorithm flow. So in each communication round, the selected clients train locally using stochastic gradient descent and send the updates to the server. The server constructs the state vector from these gradients and feeds into a DRL agent. The agent outputs values for alpha 1 and alpha 2, which are used in server model update formula. This allows the model to update more intelligently, leading to improved learning performance. And let's move to the next slide. And let's see state, action, and reward design in Federal. Federal's DRL agent uses a well-structured state, action, and reward design. The state is the element-wise square of aggregated gradients. The action consists of variation to alpha 1 and alpha 2, which guide how fast and in what direction to update the model. The reward encourages both accuracy and efficiency computed using current accuracy, target accuracy, and control parameters. Let's move to the next slide. Let's see efficient state space with PCA. The state vector derived from the gradient can be very high dimension, which slow down the learning and DRL processing. So FedRL solved this problem by using principal component analysis. And the principal component analysis to reduce the state vector into the single dimension. This compression maintains the essential information and speed up the computation. The PCA model is trained once at the start and reused throughout the all rounds, ensuring an efficiency and lightweight solution. And next part will be presented by Nilmi. Thank you.
Thank you, John Copen. Now let's go to the experimental results. Under the experimental results, these demonstrate the effectiveness of FedRL in handling non-ID data across various datasets, including MNIST, EMNIST, and CIFAR-10. These findings showcase significant improvements in performance and robustness in federated learning scenarios. Move to the next slide. Go to the next slide. Under the experimental setup, the authors conducted comprehensive experiments on 3 datasets: MNIST for basic digit recognition, EMNIST for autoencoder training, and CIFAR-10 for complex image classification. They created different levels of non-ID data by varying the percentage of dominant class data each client holds from 20% in low heterogeneity to 80% in high heterogeneity settings. As the impressive performance gains, the results are striking on MNIST. FedRL reached 99% accuracy in just 38 communication rounds compared to Fed average 36 rounds. That's a 50% improvement in convergence speed. On CIFAR-10, the difference was even more dramatic. FedRL was the only method that successfully reached the target accuracy of 74%, while other methods plateaued at lower levels for the MNIST autoencoder task. FedRL achieved the target loss in 154 rounds versus Fed average 328 rounds, a 53% improvement. Move to the next slide. Under the robustness, what makes these results even more impressive is the robustness testing. The authors tested FedRL on heterogeneity levels it had never seen during training. Without any retraining, FedRL maintained its performance advantages across low, medium, and high heterogeneity scenarios. Under the dynamic environmental performance, they also tested in dynamic settings where clients generate new data as training progress, simulating real-world conditions where user behavior changes over time. FedRL remains robust in these challenging scenarios. Let's move to the next slide. Really, why this matters? These results demonstrate that FedRL addresses a fundamental limitation in federated learning. By maintaining long-term memory of the optimization process while adapting to current conditions, it achieves both faster convergence and better final accuracy. From a practical standpoint, this means federated learning systems can train better models with fewer communication rounds, reducing both time and energy cost, critical factor for deployment on mobile devices and IoT systems. As the conclusion, FedRL represents a significant advance in federated learning by solving the memory loss problem through intelligent reinforcement learning-based aggregation. It's ready for real-world deployment and opens new research direction in adaptive federated optimization. This is the end of our conference paper presentation. Thank you all for your kind attention.